everyone, welcome into lecture number 11 of Calculus 3. This lecture is on extreme values of functions of multiple variables. Let's start though by remembering the extreme value setup from Calculus 1. So we'll start by reviewing critical values, critical points, extreme values, etc. And then we'll extend this all to Calculus 3. So in Calc 1, let's recall, I'm going to do this very quickly, but let's let y equal f of x be just a function, let's say a differentiable function. Then we're going to review a couple definitions, like I said, that are going to extend to Calculus 3 in a very straightforward manner. So a critical point, so let's start with this, or a critical value, let's start with that first, critical number, let's say. A critical number of f is a number, let's call it c. So we're defining critical number such that f, so one of two things is true, right? So I'll write it here. So f prime at c is either equal to 0 or it's undefined. Right? So the derivative is either equal to 0 or the derivative is undefined. This is a critical number. So when I say this, the number c should be in the domain of f, right? So where c is in the domain of the function. Okay, then what we have is another idea here. So let's consider the graph of the function. I'm just going to sketch a graph here. Doesn't matter exactly what it looks like, but here's our y, here's our x. So there's a couple different possibilities here of the behavior of this curve. So I'm going to try to draw all three on this one graph. So let's say this is the graph of y equals f of x, and then some of the critical values here. By the way, a critical point is just the output of the point. So a critical point would be if c is a critical number, then the critical point is c f of c, right? That's a point on the graph. So if here, we'll call this one c1 in this picture. Remember, this is just supposed to be review. So if this is c1, then this is a critical point because the derivative is 0, right? This is a critical point right here because, again, if you believe my picture, derivative is 0. This one, maybe call this one C3. This one's supposed to be a critical point if you believe my drawing, because on this one, the function's defined. There's a cusp there, but the derivative becomes undefined, right? So the point is defined. The point is on the graph, but the derivative becomes, the tangent line becomes vertical, and so the derivative is undefined. All right, so all of these, by the way, correspond to local max, local min, local max, right? So local means that in nearby it is the highest or lowest point on the graph. So these are all local extreme points. However, there's another one here, and this one I'll do a different color. Call this one C4 on this picture. Around here, the idea, if I drew this correctly, was that the curve should have leveled off, all right, and had a 0 derivative at this point, but this point is kind of just a stagnation point, just kind of mellows out, has a horizontal tangent line, but then it doesn't have a max or a min here. So again, if we're to zoom in on this point, then what this looks like is at this point the curve is above the tangent line and then below the tangent line, but at this point the tangent line becomes horizontal. So this is the idea here. And so this is a point, this is a critical point that corresponds to neither a max nor a min of the function. All right, and so one more thing I want to review from Calc 1, and then we'll go to Calc 3, and we'll generalize all these ideas to functions of multiple variables. But there's an important theorem that relates the critical points of the function to the local max and mins of the function. So notice in this picture we have 4 critical points, right? There's only 3 local max and mins based on the way I've drawn this, but every one of those local extreme points, so the local max and the local min points, those all correspond to critical points of the function, whereas even though this is a critical point, it's neither a max nor a min, right? So this becomes a one-way theorem, but this theorem is due to Fermat, and I hope you remember this one. If f has a local max or min, so a local extreme point at a point a, b, all right, then this point, so then, oh, sorry, we have to say, no, this is fine. So then AB is a critical point. A critical point of f. All right, so this is for Moz theorem. What this says then is that if we're trying to locate the local max and min points of our function, then we can look for the critical points. We still then have to check whether they're max, min, or neither, right? But this says that if the function has a local max or min at AB, then AB is a critical point of f. All right, and so remember, this means that the point is in the domain, so critical number, critical point here, means that the x value is in the domain of the function, and the derivative is either 0 or undefined, right? So it's either 0 or undefined. Okay, so let's extend this now to calculus 3. So now let's suppose that we have a function of more than one variable. Let's just do 2 variables for now. So we'll say extending to calculus 3. And here's how it's going to work. So let's first define our critical points, and then we can extend for Moz theorem, and then we'll draw some pictures. Okay. So here's our definition of a critical point. So remember, we have a gradient vector now, right? So let's let f be a differentiable function of 2 variables. So of 2 variables, I'll just write it like this, x and y. All right, a critical point of f is a point x naught, y naught, f of x naught, y naught, such that x naught, y naught, obviously just because of the way I wrote it, right, it has to be in the domain of f. So the domain point, obviously it has to be in the domain, so that is a given here. So it has to be in the domain of f, and one of 2 things is true. So either the gradient of f at x naught, y naught is equal to the 0 vector. Okay, remember, critical point up here meant the derivative is 0. So the gradient is the analogous thing to a derivative in for these functions of 2 dimensions, or 2 variables, or the gradient vector is undefined at this point. All right, so same deal. So this gives us a critical point of our function f of more than one variable, because this could extend to more than 2 variables even, right? But for the sake of this argument, let's leave it as a function of 2 variables. All right, so let's remember what the gradient is. Now, so that's our definition, right? We can leave that there. But recall that the gradient vector of our function is itself, it's a vector field actually, right? So it's a vector whose components are functions themselves, and these functions are given by the partial derivatives of their function f, right? So df dx and df dy, those are the component functions of the gradient. And so if this is going to equal the 0 vector, then what does this mean, right? So since this is the formula for the gradient, then here's what this implies, that the gradient of f equal to the 0 vector implies that actually both partial derivatives, df by dx, is equal to 0, and at the same time df by dy is equal to 0. So both partial derivatives are equal to 0. So let's think about geometrically what this means, right? So geometrically, this would mean if our gradient vector is 0, is the 0 vector, then that means that the tangent plane to our surface at any of these points is going to be parallel to the xy plane. And so that's what we can regard that as horizontal, right? If we go back to our Calc 1 analogy, then horizontal tangent line is going to correspond to tangent plane that is parallel to the xy plane, right? All right, so here's a couple possibilities. So I'm going to draw the tangent plane. All right, there's a tangent plane. So and this is supposed to be, I'm not going to draw the axes for every example that I'm about to sketch here, but let's suppose, so that tangent plane is supposed to look like it's parallel to the xy plane here. So there's our tangent plane. And let's say that this point near the center of the portion of the plane that I've drawn, so this is our tangent plane, right? This is the point on the curve, and let's suppose that the curve, by curve I mean the surface actually, right? The graph actually curves away and sits entirely below. So near this point, the surface sits entirely below the tangent plane. So if the surface sits entirely below the tangent plane, then that point is going to be a local maximum, right? So here's, I'm going to just sketch these cases here, but here we have that again. So if the surface is entirely below the tangent plane, then P is a local maximum. It's the highest point nearby, right? It's the peak of the little hill that it lives on. So this is a local maximum. All right, so this point, so in this scenario, because the two partial derivatives are both 0, right? So horizontal in this direction, horizontal in this direction, and the curve, each curve in those planes sits below it, so it looks like Calc 1, it looks like local max in both directions. Then actually the entire tangent plane sits above this portion of the surface, and therefore it's a local maximum, right? But this does correspond to gradient equal to 0. Now the exact opposite situation here, right, would be that our point sits entirely below, or our surface sits entirely above the tangent plane, or the tangent plane is entirely below, right? And so in this scenario, our surface near the point is going to look something like this, right? Just nearby, locally, near the point P, and near this point now, our tangent plane sits entirely below. There's our tangent plane, and so this is going to become a local minimum, right? So I'm not going to rewrite all of this, right? But in this scenario, so tangent plane entirely below corresponds to a local minimum of the function. So local minimum of the function f. Remember, the blue here is the graph of the function f. All right, well, there's other possibilities. And by the way, I drew this so that in both of these cases, these correspond to gradient equal to 0. What would gradient undefined look like? Well, let's do one where it's a local max, very, again, analogous to our picture up here. So we've drawn now this and this in the analogous two-dimensional, right, surface versions. What about this cusp? What would this cusp look like on a surface, right? Well, near this point, again, there's no tangent plane here, because what we're going to do is we're going to have a point where the surface comes to a point, right? It approaches this point. And so nearby, maybe it's like a pinhole, right? But there's not a hole there, but it's like you've pinched it and you have a nice pinched cusp here. So this is called a cusp. This could be a local min or a local max, but at this point, the gradient of f is undefined, right? There's no tangent plane at this point because it's not smooth, right? It's not smooth. So the gradient is going to be undefined at this point. So this is called a cusp. This is still, the way I've drawn this one is still a local maximum. If I drew this upside down, it would become a local minimum, right? So there's an example of gradient undefined, so it's still a critical point, right? And it is a local max in this case, or it could be a local min if this picture is flipped upside down. All right, what about the case where it's neither? Well, again, let's think about so in this case, this is our last case that we'll do before we just state the results, but the gradient f equal to 0, all right, but not a max or min. So not a local extreme point. So local extremum. So in this scenario, again, if the gradient vector is equal to 0, then that means that the tangent plane to the surface at the point is going to be parallel to the xy plane. So that's horizontal in the sense that we're considering it here, right? But for this to not be a local extreme point, what does that mean? Well, it means that in one direction, the surface is curving above. So there it would look like a local minimum, right? This would be a local minimum point if this direction was representative of the entire surface. On the other hand, in the other direction, the surface may be curving below, right? And so in this case, that would be a local maximum. Well, it can't be both, right? And so this is neither a local min nor a local max. And if you try to envision what this surface is going to look like near this point, where the two slice curves, right, in the partial derivative directions look like this, then I think you'll be able to imagine that this portion of the curve has to look like one of our hyperbolic paraboloids. So it has to look like a saddle, right? So this portion would look like a saddle. Near this point. And so the idea is here, the tangent plane sits above the curve, the surface in one coordinate direction, but it sits entirely below the surface in the other coordinate direction, and therefore this is neither a max nor a min. So neither a max nor a min in this situation. All right, and this is, again, this is called a saddle point. And saddle because of the shape of the hyperbolic paraboloid at this point, right? Okay, so let's state an extension of Fermat's theorem then. It's going to be exactly the same, but in this context of functions of more than one variable. So this is Fermat's theorem extended. All right, and here's what this one says. It's going to say if f has a local extreme point, so local extremum at a point AB, and the first order partial derivatives exist, so first order partial derivatives exist at this point, again at this point that we're considering, right, at this point AB, then what's got to be true about them? Well, if they exist, then we can't include the undefined version of our critical point, right? So if they exist and we have a local extreme point, then it's going to have to be that the gradient is 0. But we can write this in terms of just the partial derivatives themselves. So df dx at AB equals df dy at AB equals 0, right? Both of the partial derivatives in the coordinate directions equal 0. Okay? So this is an extension of Fermat's theorem because, again, we have two things, right? Number one, if they exist. If they don't exist, then the gradient is undefined. So if they do exist, then the gradient is 0 in both components. So that's exactly right, right? So we can rephrase this as or, right? Or if f has a local extremum at AB, then AB is a critical point. The way we've defined critical point, this should be AB and then f of AB, right? The point on the surface. So this is a critical point. All right, and so this is just that is exactly the way we stated it in Calc 1, right? So this is an extension, as long as we understand that we're now working with surfaces instead of just graphs, curves, right? Curves in on a two-dimensional plane, the xy plane. All right, so let's try an example now. So for this one, here's a function, f of xy equals x squared minus y squared plus 2x plus 6y plus 14. So what I would like you guys to do is find all critical points. So find all of the critical points. And then, if possible, determine whether they're max, min, or neither. So determine if they are extrema. All right, so why don't you guys take a minute, try to follow the definition. You're going to obviously take the gradient and think about the gradient, think about this function. Once you look at the gradient, think about whether or not it can even be undefined, and then find the critical points, plug in, and see what you get. So take a minute, work on this one, and I'll check back in with you in a minute. Let's see how you did. The first step of this problem is going to be to compute the gradient. And remember, the gradient is just the vector of partial derivatives. So the gradient I've been saying is a vector field. We'll define this formally later, but for our sake right now, it means that it's a vector whose components are partial derivatives. So we take the partial derivatives of this function. They're very straightforward, right? So this is 2x plus 2 in the x component, and it's minus 2y plus 6 in the y component. This is, as a function, right, individually, these component functions are very, very nice, and they actually can't be undefined, right? And so the only possibility here is that our gradient vector could equal the 0 vector. So at this point, we can set the components equal to 0. We get two equations, right? 2x equals 0, negative 2x plus 2 equals 0, negative 2y plus 6 equals 0. This is technically a system of two equations and two unknowns, but the two equations are each of a single variable. So here we can see that x has to be equal to negative 1, right, to make that be 0, and that y has to be equal to 3. And so we get one critical point, right? So the critical point of this function f is, in this case, it's going to be negative 1, 3, and then we need to plug in, right? So f of negative 1, 3. And we need to then determine whether or not this is a max, a min, or neither. So let's first compute the value here, f of negative 1, 3. We plug in, we're going to get negative 1 squared minus 3 squared plus 2 times negative 1 plus 6 times 3 plus 14. And so this is 1 minus 9 minus 2 plus 18 plus 14. All right, and so this is going to be what, 22, I believe. Hopefully I computed that right. It's 1 minus 11, so negative 10, 8, 22. Yep, that's good. So now the question is it a local max, a local min, or neither? And for this, we can look at this, we can think about this surface, right? We can think about this surface and think about its graph. So this surface, let's write down the function again down here. So f of x, y is equal to, so it's equal to x squared plus 2x. I'm going to kind of rearrange this, and then I'm going to write over here minus y squared in parentheses minus 6y parentheses, and then leave some room, put plus 14. And so I am going to complete the square on this, actually. So this one needs a plus 1 to complete that square. This one needs a plus 9 to complete that square. But obviously, if we do this, we need to subtract away the 1 that we add here. And we need to add, actually, the 9 that we add here. We subtracted a 9, actually, right? And so what we end up with is that this is going to be x plus 1 quantity squared minus y minus 3, right? Quantity squared, and then when we add this up, we get what? 22, right? And look at these numbers are not a coincidence, because we have negative 1 plus 3, 22. Those are exactly the numbers, right? The components, coordinates of our critical point. And we see that we know that this function, right, if z equals this, then this function is going to be a hyperbolic paraboloid, right? So it's a hyperbolic paraboloid because of this minus sign. And so we know that this graph looks like the picture that we drew up above with the saddle point. It might be curving the other way. I think it is. So let's draw it the right way. So this one's going to be in the x, y, z space. Right? The point that we know we're working with is x equals negative 1. So that's back here, right? Negative 1, y equals plus 3, and z equals 22. Right? But from this point, in the x direction, our surface is curving upward. Right? It's curving upward. And in the y direction, our surface is curving downward, the negative sign here, right? Might look something like this. And so altogether, that's going to be a saddle point, right? So this critical point corresponds to a saddle point of the surface. So neither, remember, saddle point means neither a max nor a min. Neither a max nor a min. All right, so the next thing that we'd like to talk about is once we've located a critical point, do we have to actually sketch the graph like we just did for this example? This function was pretty nice, right? So comparatively, compared to some functions that we've encountered. So it was possible for us to just imagine what the graph looks like at this point to determine whether our critical point was a local extreme point or was it a saddle point, right? But in general, we're going to want a better way to do that. And the better way is going to be an analogy of the second derivative test from Calc 1. So I'm not going to rewrite the second derivative test from Calc 1. I will write the new one for Calc 3. But you guys should go back and review the second derivative test from Calc 1. So we're going to set this up by first defining a special function, a special matrix function actually. But let me write this title first. So the second derivative test. All right, so like I said, before I state the second derivative test as a theorem, I want to define some new functions here. So let's let f be a function of two variables, all right, with continuous second partial derivatives. So once you hear continuous second partial derivatives, you should automatically be thinking about one of our favorite and most important theorems. All right, and so I'm going to add to this on an open set. And this open set is going to contain some point that we care about, which is probably going to be a critical point. You can probably guess that, right? But so we have a function f of two variables whose second partial derivatives are continuous. Then we can define something called the Hessian matrix. So the Hessian matrix of f, this is what we're defining. The Hessian matrix of f is, in some sense, it's very similar to the gradient vector field in that it's like a matrix field. We don't need to get into what these are called in other areas of math, but for us, this is the only kind of matrix function like this that we're going to study, and we're only going to do one thing with it. So let's just write it down, and then we'll deal with it from there. But I'm going to call this h with a hat sub f. But again, it depends on the variables x and y. So it's going to be a matrix of functions, and the entries are going to be the partial derivatives, the second partial derivatives of our function f. So it's going to be the second derivative of f with respect to x twice in the first 1 component here. The second derivative of f dy by dx. So the first column here is the mixed derivatives of the x derivative, right? So those are the second derivatives. Up here, the next second derivative is going to be the second derivative with respect to x after with respect to y, right? So dy, so it's dx dy as you read it, right? But remember that we work from right to left with these derivatives in this notation. So that's the mixed partial dx dy. And then the last component here is going to be the second derivative with respect to y twice. So this is a matrix, a 2x2 matrix. So it's got 4 functions in it, and those 4 functions are an arrangement of the second partial derivatives of our function f. All right? Now, I said we're only going to do one thing with this, and the one thing that we're going to do with this is we're going to take its determinant to make what we call the Hessian function. So the Hessian function, also sometimes just referred to as just the Hessian, for us at least. So I'll write Hessian with function in parentheses, sometimes called the Hessian determinant, but we're just going to call it the Hessian probably moving forward. Of f, this is the function. Now we'll just call this h sub f of xy. So drop the hat, right? This is going to be the determinant of h with a hat xy. And determinant, we probably remember from cross products, etc. So there's other things that we've calculated at the end of Calc 2. The determinant for a 2x2 matrix is just a product of the main diagonal minus the product of the off diagonal. And so the product of the main diagonal is going to be the product of these two second derivatives in the coordinate directions, right? So d squared f dx squared times d squared f dy squared. And then we need to subtract off the product of the off diagonal. But now this is where the continuous second partial derivatives comes in. By Clairaut's theorem, that's the theorem I referred to earlier, or alluded to earlier. By Clairaut's theorem, these two partial derivatives are going to be equal, right? Because second partial derivatives being continuous means that the mixed second partials are equal. So we can actually write this as the second partial derivative dx dy, or you can do dy dx, doesn't matter, but either one, your favorite one, squared. Okay, so it's the products of the two coordinate second derivatives, so d squared f dx squared times d squared f dy squared minus the mixed partial second partial squared. All right, and that's the Hessian function of f, so that's h sub f. All right, so let's now state a theorem. So again, this is the main reason for even defining that matrix Hessian, just because we're going to take its determinant and we're going to work with this. All right, so here's our theorem. This theorem is the second derivative test for functions of multiple variables. So it's a theorem, but it's our second derivative test. All right, we need to always state hypotheses when we state a theorem. We start with hypotheses. So let's suppose that AB is a critical point of f. So we've already located the critical points, right? This means that the gradient is 0, right? Or undefined. It's either 0 or undefined. So it's a critical point of f. And further, f is continuous on an open set containing this point. So we have to write all this out, but open set containing our point AB. Then the following are true. There's three different possibilities here, okay? So if our Hessian function at the critical point, if hf at AB is greater than 0, and the second partial derivative in the x component only at AB is also greater than 0, all right, then our point f of AB, our critical value here, right, this is a local minimum of the function. So this is a local minimum. All right, so the idea here is the Hessian is positive, all right? Hessian is positive. That means that it's defined as well, right? So the Hessian is positive, and the second derivative in the x direction is also positive. Then this means we have a local minimum. So basically, what is this saying? There's two more cases, but before I get to them, I want to go back to our pictures. Basically, it's saying this, right? So what the Hessian is measuring is that the two coordinate directions, if the Hessian is positive, it's saying that the two coordinate second derivatives are curving the same direction. So the curvature is in the same direction. And then if the x one, so that's the one coming out of the screen at you, right? If that one's positive, then it means they're both positive, and therefore the whole surface sits above the tangent plane at this point, and we have our local minimum, right? We can flip that over. So the Hessian positive, but the second partial is negative, is going to mean that the tangent plane sits above the whole surface. And then we'll get to the last one in a moment here. But this case 2 is going to be very similar here. So if our Hessian is positive and the second derivative in either coordinate direction, so this says x twice, but you could do y. If this is negative, then that means that our point, right, our value is a local maximum. All right, so the second derivative test, positive second derivative, negative second derivative, these are what we're used to, right? Now, both of those depend on the Hessian being positive. So the third case is going to say, what happens if the Hessian is negative? So if the Hessian is negative at AB, then the point AB, f of AB, is a saddle point. So Hessian negative tells us that our point is neither a max nor a min. So I'll just write that here, right? Neither max nor min at this point. So again, the Hessian is measuring the relationship between these two second partial derivatives in the coordinate direction. So if one is curving down and the other is curving up, then that's going to give you a negative Hessian. A negative Hessian. So just like this, right? A negative Hessian is going to happen when the curving happens in opposite directions, and therefore your tangent plane is kind of splitting through the surface at this point. If they're going in the same direction, whether both up or both down, then your Hessian is going to become positive. It's going to be positive at this point. So that's the second derivative test. Now, and that's the end of it. So I've stated all three possibilities. Notice that there's a possibility that's missing, right? So if the Hessian is equal to 0, what do you think our conclusion is? So it's going to have to be that the theorem does not apply, right? Because there is no information given here if the Hessian is equal to 0. So this is an implicit observation. It's not written. I'm making it explicit, right? But as you read this, you should have noticed that it's implicitly, right? This is actually a result. So if h of f a b, so if the Hessian is equal to 0, then the second derivative test does not apply. You cannot draw any conclusions if your Hessian is equal to 0. Then you have to go back and use like a first derivative test or try to sketch the curve, the surface, like we did on the last example. Okay, so that's the second derivative test as a theorem. It is a theorem. Let's now do another example. So here's a function, f of x, y equals x to the fourth plus y to the fourth minus 4xy plus 1. So on this one, I would like you to do the same thing that we did on the last one. So find all critical points and classify them. So this time use the second derivative test to classify them. All right, so take a few minutes, find the critical points, classify them using the second derivative test, and when we check back, we'll check your answer. All right, let's see how you did. Let's start by taking the gradient of our function f. So the gradient, remember, is the vector of partial derivative functions. So this is going to be 4x cubed minus 4y in the first component, and then 4y cubed minus 4x in the second component. And we want to set these equal to 0, right? So to find the critical points, it's not ever going to be undefined because these are polynomial functions. So gradient f equal to 0 vector is going to give us two equations with two unknowns. So 4x cubed minus 4y equals 0, and 4y cubed minus 4x equal to 0. And let's see if we can solve these. So the 4's cancel, right? And we'll get from the first equation that x cubed equals y. The second equation we get, right, that y cubed equals x. And so we can kind of do some substitutions here, either way that you want to go. But if let's go in this direction. If y equals x cubed, we can plug into here, and so then we get x cubed equals x. And so this is going to give us that x to the 9th equals x, or x to the 9th minus x equals 0. All right, and by factoring this, we get x times x to the 8th minus 1 equals 0. This has a number of complex solutions, but it's only going to have 3 real solutions, right? So 3 real solutions. And the real solutions are that x equals 0, x equals 1, and x equals minus 1. So those are our 3 solutions for x, right? Now we need to plug back in and find the y values. So once we know our x values for our critical points, then we can find our y values by plugging into here, right? They have to obey this relationship. So our critical points then, I'll write it over here, our CPs are going to be, I'll just write the x and y coordinates of these, but when x is 0, y is equal to x cubed, so y is 0, right? So there's one of them. When x is 1, y is equal to 1 cubed, so it's equal to 1. So there's another one. And then third, when x is equal to negative 1, y is equal to x cubed, so it's also equal to negative 1. And that's it, right? So if you had done the same analysis and found the y values, you would find 0, 1, negative 1. And you might think that you can take any combination of those points, right? Those 0, 1, negative 1, but you can't, because they have to obey this relationship, which is going to give you the 0 gradient vector, right? The 0 gradient vector. So these are our critical points. These are the points that we now have to analyze our second derivative at, okay? So these are the critical points in the domain. So we can leave it here. We can plug into the function if we want. So let's do it. f of 0, 0 is going to be just 1, right? Just plug in, you get 1. f of 1, 1, this is going to be 1 plus 1 minus 4 plus 1. So that's going to be minus 1, right? 3 minus 4. And f of negative 1, same deal, because actually positive 1, those cancel, become negative 4, so this is also negative 1. So the critical points as points, right, are going to be 0, 0, 1, 1, 1, negative 1, and negative 1, negative 1, negative 1. All right, let's classify them now. So the classification comes from the Hessian. So we need to compute our Hessian matrix first. This, remember, is the matrix of second derivatives. And we can, because, well, we need to check, but we can just write these as the same derivative, the same mixed partial, because this function's a polynomial, right? So the second derivatives are going to be nice, well-defined. So now we take the second x derivative. That's going to give us 12x squared minus 0, right? So this is 12x squared. We take our mixed partial derivative. That's going to just be the y derivative of the x component, right? That's going to be negative 4. So negative 4 actually goes here and here, right? And then we take our y, our second y partials. That's going to be 12y squared minus 0. So 12y squared. So there's our Hessian matrix. Now, and you can check, by the way, that your x derivative of the y derivative is also negative 4. So even though we kind of cheated, that we didn't cheat, right? But we took advantage of Clairaut's theorem, and it turns out, you know, it would have been just as easy to compute both derivatives. But Clairaut's theorem definitely applied. We got the right answer. All right, so now we need to take our Hessian determinant, right? So our Hessian function is actually going to be 144, 12 squared, times x squared times y squared, minus, right, this product, or just one of these squared, so minus 16. So there's our Hessian function. Now we need to plug in the values for each of our critical points. So our Hessian at 0, 0 is going to be equal to negative 16. All right, just plug in the zeros, negative 16. This is less than 0, so what's our conclusion? Well, our conclusion is that this point, 0, 0, 1, is a saddle point. When the Hessian is negative, the surface has a saddle point. So there, we've classified that critical point, right? What about the other two? Let's check them. HF at 1, 1. This is going to be the same as negative 1, 1, but let's just do this one first. This one is going to be, if we plug in, we get 144 times 1 times 1. So 144 minus 16. You can do the math here. This is 128, but the point is that it's positive, right? So this is either a max or a min, but which one is it? It's not clear, right? So we need to now check the second derivative, and we have a formula for the second derivative already here. And you could use either one of these, right? Either one of this one or this one, but let's just focus on the x one. So obviously, the second derivative in the x direction twice, when x and y are both 1, this is going to be equal to 12 times 1 squared. So that's 12. That's positive. So if these are both positive, then our second derivative test tells us that this point, 1, 1, minus 1, is a local minimum. Right? If they're both positive, we have a local minimum. And then similarly, the same thing's going to be true for the other one. I won't write this one out. But similarly, negative 1, negative 1, negative 1. This point is also a local minimum. All right, so that's how this works. Now, just given this information, we can sketch a little bit of the surface here. So the surface is going to look something like, there's these three critical points, right? And everything is curving upward. Local minimum, but in between, right, we have something like this. So the surface is going to look something like this, where we have, again, our local minimums here, right, and our saddle point in the middle. This is the one that's above the origin in the xy plane. So this is pretty much what the surface is going to look like here. It's going to have a little bit of it's all curving upward, right? Except for in between these two local minimums, where we end up with this saddle point in between the two. Okay, so that is an example of how we can use the the second derivative test to help us compute or classify our critical points, right? So we've classified our critical points. The next thing that we want to talk about is the extreme value theorem. So the extreme value theorem, I hope you remember from Calc 1. This applies to continuous functions on bounded intervals, right? So it says that in Calc 1, it says that a continuous function on a bounded interval, right, where the endpoints are included, attains a an absolute maximum and minimum on that interval. So this is going to be the same situation, except now our domain is not going to be an interval. So I'll state it as a theorem. This one says the following. If f is a continuous function of two variables, we'll say, again, so of x and y, on a closed, bounded set, D, we'll call it D, in R2. Closed and bounded means that you can draw the boundary and it includes the whole boundary, basically. So then the conclusion is then f attains. This is the key. It actually reaches, right, an absolute maximum and an absolute minimum value. So it attains an absolute max and an absolute min on this set D. Okay, so I'm just going to state this without proof, but the idea is that now what do we have to do? We have to check for, so where could they be, right? Where could the local max and local min be? So the extreme points, so the plural of extremum is extrema. The extrema could be in two places, right? They could be, one, at critical points in the interior, so at critical points, or two, they could be on the boundary. So if our domain looks like some kind of wacky shape, right? So if this is our domain, and there's the interior, and we've got a continuous function defined on here, and let's say there's a couple critical points, right? Those are the critical points. Then we need to check the extreme, to find the extreme values, right? We need to check the values of the function at these critical points. So locate the critical points, check the critical points, but then also check the values on the boundary itself. Because it could be that the function is, higher, or these could just be local extreme points on the interior, and the actual absolute extreme points could be on the boundary. So that's our kind of plan of action, just like Calc 1, right? So just like Calc 1, we're going to check critical points within the domain, and then we're going to check the boundary as well, and we're just going to take the largest and the smallest values to be our absolute max and min of the function. All right? So let's do an example. So for this one, let's try to locate, so find the absolute extrema, max and min of this function. So this function is going to be f of xy equals x squared minus 2xy plus 2y on the rectangle. So this domain is going to be a rectangle. So I'm going to define it as 0, 3 cross 0, 2. So this means that as far as the domain is concerned, the domain in the xy plane, right, goes from 0 to 3 in the x direction and 0 to 2 in the y direction, and then of course this is going to fill out an entire rectangle. So there's our domain D. Okay, so take a moment, try to locate the absolute extrema of this function. So the local, you're going to try to find critical points. If you find a critical point We only care if that critical point's within D, right, within the domain. Check that, and then check all the boundary. And try that on your own, check back, and we'll do it together. Alright, let's see how you guys did. So the first step, as we said, is to try to locate the critical points. So we need to take the gradient. The gradient vector for this function is going to be 2x minus 2y, and then it's going to be negative 2x plus 2. Right? Take the y derivative. Alright, if we want this to equal the 0, again, this one can't be undefined, right? So we want this to equal the 0 vector. Then what we end up with is a system of equations. 2x minus 2y equals 0, and negative 2x plus 2 equals 0. So this one tells us that x has to be equal to 1, and this one tells us that x has to be equal to y. So therefore y is also 1. And so the critical point of this function is at the point 1, 1, right? So this tells us then that 1, 1 is the only, right, critical point. So now what do we have to do? Well, we have to check the value of that. So let's compute f of 1, 1. This is going to be equal to 1 squared minus 2 times 1 times 1 plus 2 times 1. All right, and so this is just 1, right? So minus 2 plus 2 plus 1. So there's just 1. Now what we also have to do is check the boundary. We have to check the boundary. So let's consider there are 4 components of the boundary now, right? So we have to consider each component of the boundary, and then just see what happens. So let's say component 1 is going to be the component. Let's just do it this way. Let's say when y is equal to 0, right, then x varies from 0 to 3. So now we've got a extreme value theorem from Calc 1, because our function f of x comma 0 is going to be equal to what? Well, if y is 0, then our function is just x squared, right? Our function is just x squared. And then on the interval from 0 to 3, we know that x squared is increasing, and its maximum value, right? So in other words, the points that we're going to care about are f of 0, 0 is equal to 0, and f of 0, 3 is going to, 3, 0, sorry. F of 3, 0 is going to be equal to 9. Okay? And so those are the maximum and minimum values of our function on that boundary, on this boundary down here from 0 to 3. The boundary of the rectangle, right? There are 3 other boundaries to check. So the next boundary to check is when x is fixed equal to 3 and y varies from 0 to 2, right? So now our function f of 3y, this is going to be equal to 9, and then 3y, right? So it's going to be minus 6y plus 2y. So minus 6y plus 2y is minus 4y, right? So minus 4y. And again, this is a linear function, and it's increasing. Decreasing, actually, right? So it's decreasing, but the point is that we just have to check the endpoints. So f of 3, 0, we already know what that is, right? That's going to be 9. F of 3, 2, that's the other boundary point here. That's going to be 9 minus 8, so that's 1. All right, and then we just continue this process. So the next component that we can look at is fix y equal to 2, boundary component. X varies from 0 to 3, and so our function is going to be f of x comma 2, and so in this case we have x squared minus 4x plus 4, right? So x squared minus 4x plus 4, and so we plug in again, right? So f of 3, 2, that's still going to be 1. Right? F of 0, 2 is the other point to check. F of 0, 2 is going to be 4. Okay, and then one more boundary to check. So the last boundary to check is x equals 0, y varies from 0 to 2, and so f of 0y, this one's going to be what? When x is 0, we end up with just 4y, right? When x is 0, sorry, 2y. So our function is just 2y. Again, it's linear. We check the boundaries. We already know actually what the points are all equal to, right? So f of 0, 2 is equal to 4. F of 0, 0 is equal to 0. All right, so now we have collected all of our max mins along the boundary components. We have collected our critical point on the interior, and at this point all we have to do is look at the values of these, right? So of all these numbers, the largest number is 9, right? And the smallest number is 0. And that's the answer then. Okay, so that's it. So 9 and 0. So this value of 1 is not going to be either a max or a min. Okay, so now we just summarize and we say that the absolute max of f on D is 9, and the absolute min is going to be 0. Okay, and so that's that. All right, so for the last little section of this lecture, let's talk about optimization. So let's consider the following motivating example. So let's suppose a rectangular box with no top, so without a top, is to be made from 12 square meters of cardboard. All right, so 12 meters squared of cardboard. We want to find the maximum volume of such a box. And there's many ways to do this, but we're going to do this a couple different ways actually. We want to find the maximum volume of such a box, all right? So the box itself looks something, you know, it's just a rectangular box. All right, so in this scenario, let's think about the coordinates here, the components. So we have our x in this direction, right? We have our y, which is actually in this direction usually, right? So there's our y. And then we have our z in this direction. And so we know a couple of things. Number one, the volume is what we want to maximize, right? So the volume is a function of all three of these, x, y, and z, and it's just given by the product, x times y times z. And we also have a constraint here. And so this is what we're going to focus on now, optimization with a constraint. The constraint is going to be that the surface area of this box is going to have to be equal to 12, right? But the surface area includes only 5 surfaces, not 6, right? It does not include the top. So there's no top on this box. So our surface area constraint, A of x, y, z, this is going to be equal to x times y, the bottom, the area of the bottom, plus the surface areas of the sides added up, right? So there's 2 copies of x times z, the right and the left, plus there's 2 copies of the faces z times y, right, the front and the back. So 2 times y times z. And this has got to be equal to 12. So this constraint here is the key. All right, this constraint is going to be the key. All right, so again, this is to be optimized, TBO. To be optimized is our function v, and our function a gives us a constraint. So we have a fixed value of this constraint, right? So let's think about how we can actually solve this. One thing we can do is we can take our constraint function and we can solve for one of the variables, right? So let's take this and solve for z. You can do it for any variable, but let's do it for z. So if we do that, then what we end up with is z times 2x plus 2y is equal to 12 minus xy. And so this tells us that z itself is equal to 12 minus xy divided by 2x plus 2y. And by the way, we have physical constraints as well, right? This box, the volume is not going to be maximized if any of the components, x, y, or z, are equal to 0. So especially not if they're both, x and y are both equal to 0, right? So in this scenario, 2x plus 2y is not going to be 0 because just for physical reasons, and even just by investigating our function, there's no way that that's going to give us the maximum, right? So we exclude that possibility from the very beginning. All right, so this is now a formula for z. We can plug this back into our function v, right? So v can be reduced to a function of 2 variables. V of xy is now going to be equal to x times y times 12 minus xy over 2x plus 2y. Whoops. And this is now a function of two variables that we can optimize the same way that we just did, right? So now this function can be optimized just like we've studied in the previous examples. All right, so what do? Well, we look for a point where the gradient of v is equal to 0, or maybe undefined, but equal to 0, right? So find a critical point, and then once we find that critical point, check it, right? Check on it. Make sure that it's actually a maximum. Okay, so let's do it. So let's multiply through. We're going to have to take some partial derivatives here, right? So our function v of xy is going to be equal to 12xy minus x squared y squared over 2x plus 2y. So dv by dx is going to be a quotient rule, right? So quotient rule says below 2x plus 2y times derivative of the top with respect to x. So that's going to give us 12y minus 2xy squared minus the numerator 12xy minus x squared y squared times the x derivative of the denominator, so that's 2, all over 2x plus 2y quantity squared. And now we just have to try to carefully, right, work out this numerator here. So dv by dx is going to be, if we multiply through, we're going to be able to take out a 2 from here and a 2 from here. Well, let's just multiply it out and see what we get. So this is going to be 24xy minus 4x squared y squared plus 24y squared minus 4xy cubed. And then over here we're going to have minus 24xy plus 2x squared y squared. This is all over 2x plus 2y quantity squared. And then we simplify. So dv by dx is going to be what? Combined like terms, right? So 24xy, 24xy, those are gone. We can combine our x squared y squared terms. So there's going to be negative 2 of those, and then we have all the rest of this, right? So this is going to give us 24y squared minus 4xy cubed minus 2 x squared y squared. Again, all over the bottom. 2x plus 2y quantity squared. And then we see we can take out a y squared from all this, right? So y squared, we can take out actually 2y squared. And we're left with then 12 minus 2xy minus just plain x squared. And this is all over 2x plus 2y quantity squared. Okay? So at this point, we can work out dv by dy. If we go back up and we compare this function is symmetric with respect to x and y, right? If we replace x and y in this function, we get the exact same function back. So that means that the function with respect to y is going to be exactly the same, except just replace the x and the y. So this is recommended that you work this out, but this should end up being 2x squared times 12 minus 2xy minus y squared, all over 2x plus 2y quantity squared. All right, and so now these two derivatives are going to be 0, right? Only if their numerators are 0. And for the numerators to be 0, we don't want x or y to be 0. We already have established that, right? That neither x nor y should be equal to 0 itself. And so the two equations that we get are that this should be 0 and that this should be 0. So those are our two equations. So we obtain, at this point, that 12 minus 2xy minus x squared should equal 0, and 12 minus 2xy minus y squared should be equal to 0. And look what happens if we subtract these equations, right? So we have two equations, two unknowns. Subtract them, and what do we get? We get that x squared has to equal y squared. right? Because if you add these up, you'll get negative. If you subtract these as they're listed here, you'll get negative x squared plus y squared equals 0. So how can this be true, right? Well, there's a couple different possibilities. So this means either, so okay, let me sorry, now we plug in, right? So now we have that x is either equal to plus y or x is equal to minus y, right? So either x is equal to y or x is equal to minus y. Those are the two ways that this can be true. Now, neither of these can be 0, and because they represent distances or lengths, neither one can be negative either, right? So actually, this one is not the possibility. This one is the possibility, right? This is the only possibility. So x equals y is our solution. And then we go back to our original function, and we plug in x equals y, right? And we optimize. So we plug in. We plug in x equals y. Plugging in x equals y, we obtain that our function v of x is now equal to x squared. So v of x is now going to be equal to, x squared times 12 minus x squared over 4x, right? So x squared times 12 minus x squared over 4x. And so with a little reduction here, this one's just going to give us 3x minus x cubed over 4. All right. And so at this point, we can just optimize this function using our regular calc 1. So v prime of x, this is going to give us 3 minus 3 over 4 x squared. All right. And then this is equal to 0 if what happens? So this 3/4 x squared equals 3, or x squared equals 4, right? And so this gives us then that x has got to be equal to plus or minus 2. We know then that x has to be positive 2 because it's got to be a positive value. Just plugging in, we see that that's going to give us a maximum, right? So we can plug in now. We'll see. We'll check it in a second. But based on all of this, we then have, well, our y must also be 2. Right? Our y must also be 2. And what about our z? Well, remember, our z was given by 12 minus xy over 2 plus xy. So z is equal to 12 minus xy over 2x plus 2y. So this is going to be 12 minus 4 over 4 plus 4. This is 8 over 8, so this is 1. So our z is equal to 1. So these are our coordinates of the box. Again, you should check that this is a maximum. You can plug in here. You're going to get a positive number, right? When you plug in 2 to this function, you get 6 minus 2, so that you get 4, right? So that volume is positive. You can check that that's a maximum of this function. But these are the coordinates, right? So our volume, v of x, y, z, is maximum when when x, y, z equals 2 to 1, and so hence the maximum volume is v of 2 to 1 equals 2 times 2 times 1 equals 4, right? So the maximum volume of such a box with surface area 12 with no top is going to be 4, right? All right, so let's now think about another way that we could approach this problem. And so this next way is called Lagrange, the method of Lagrange multipliers. And so the situation is the following. So let's remember, I'm going to sketch this in 2 dimensions now. So let's consider the 2-dimensional situation. All right, so what did we have up here? We had a function of, in this case it was 3 variables, but a function that we wished to be optimized. And then we had another function for which we had a fixed value of it, right? So a constraint. So in this situation, we could consider our function v of xyz and a of xyz, both as functions of 3 variables. And we could consider this one constraint as a level surface of the function a. All right, and what we could look for then is when is the level surface of A tangent to the level surface of V, right? A level surface of V, and then what are we looking for? We're looking for, okay, what is the value of the height, in some sense, the output of that level surface of V. All right, so let me write this in the two-dimensional situation. So we have a function to be optimized. All right, so we have a function f of xy equals z, and then we have a constraint. So our constraint is given by another function, g of xy, but it's equal to some constant. All right, let's call this constant k. All right, so this is our constraint. It's equal to some constant k. All right, well, we can plot level curves of these things. So let's consider our xy plane. Number one, g, this g of xy equals k. This is a fixed level curve, right? So in some sense, this is an implicit curve. This is an equation that defines an implicit curve, and maybe that curve looks something like this, right? So maybe this is the graph of g of xy equals k. Doesn't have to be a function, right? Because it's implicit. It's an implicit function. So g of xy equals k is just some curve in the xy plane. So that's the blue one. On the other hand, we can plot level curves of the surface f. So maybe the surface f, the function f has level curves that behave kind of like this. Okay, so let's say these are level curves of our function f, and maybe they correspond, heights of k1, k2, k3, etc. And so what we're looking for, okay, we want to optimize, right? So the idea here is that we are constrained to the blue curve. So we are stuck on this blue curve, right? And we want to know at what point on the blue curve is the function f, so at what point on the blue curve are the values of the red function maximized or minimized, potentially minimized, right? And so there's a couple different places, right? So let's just focus on over here in the first quadrant. So let's forget about these portions where it kind of leveled, the curve I drew levels off in the other quadrants. But as we travel along the blue curve in the first quadrant, we see that we are cutting straight through. We're climbing right up this hill, right? If these level curves represent, say, increasing values of the z for the function f, until we get to here. So this one right here is an important point because we get to this height of this level curve and then we turn around and we start working our way down, right? And again, something's happening here. But if we stay in the first quadrant only, then this portion right here of the curve is going against the level curves of f except at all points except for this one, right? And so what we should remember, I hope, is that the gradient vectors of both of these functions are always perpendicular to or orthogonal to the level curves. So the gradient vector of f at this point is always going to be perpendicular, right, orthogonal to the red curves. So it's pointing this way. At the same time, the gradient vector of g is orthogonal at every point, and then at this point, right, notice that at that point it's going to be exactly in the same direction as the gradient of f. So what we're going to look for then, the whole idea here is that we're looking for a point where the gradient vectors of f and g have the same direction. Now, direction could mean negative, right? So we're going to say that they're parallel. So our goal here is to look for points where these two gradient vectors, gradient f and the gradient of g, are parallel. All right, and at those points, as we can see from the geometry of the level curves, at those points, those will represent local extreme points, okay? So these points will be local extrema. All right, and so then our goal is to try to find them, right? So try to find them. So what we do, so what does it mean to be parallel, right? So we're going to solve now. And this is the two-dimensional version, but you can extend this to 3, 4, whatever, however many dimensions. But in 2 dimensions, right, we obtain a system of equations. So we obtain a system of equations. I'm going to write it two different ways. So on one hand, we have our gradient f should be equal to, notice that the gradient vectors are not equal to each other, right? They are in the same direction. So that means that one of them, say the green one, is a scalar multiple of the other one, say the blue one in this case, right? So in other words, the gradient of f is equal to some constant times the gradient of g. All right, so this actually is part of the equation, part of the system. The other equation is the constraint, because we need to make sure that our g is constrained to the one level curve, not the other. So f can be on any level curve, right? But the point has to be on this one level curve of g. So the other constraint is that g of xy has to be equal to k. So that has to be on our level curve. Now, this is actually a system of three equations and three unknowns. The unknowns are x, y, and lambda. So this lambda here is a constant that is determined as part of our solution. All right, so this gives a system of three equations. The three equations are going to be df by dx is equal to gamma dg by dx. That's the x component of the gradient. Df by dy is equal to gamma times dg by dy. That's the y component of the gradient. And g of xy is equal to k. So there's our three equations and our three unknowns, right? And the value of lambda is determined as part of the solution. You don't know what lambda has to be at the outset, right? It's determined as part of the solution, and then I'm going to write if necessary, because lambda is not what we're looking for, right? We're looking for the x and the y. Sometimes it's necessary to actually compute the lambda, and sometimes it's not. All right, but the idea is once we solve for the x and the y, then those are going to be the candidates for the local max and min. All right, so, but we solve this system, then the points x, y are local max and min given the constraint, right? Given the constraint. All right, so let's try to repeat the exact same problem that we just did with this new method. So the point here is that we're going to know the answer, right? So this is our this is the last thing that we'll do in this lecture. But let's repeat the box problem. All right, so I'm going to redraw. Let's remember what we have here, right? So our situation is that we have a box with no top. We have these coordinates, right? We have our x. We have, I'm probably changing the colors. That's okay. We have our y. We have our z. All right, so I'm going to, even though I set this up in 2 dimensions, I'm going to do it with this 3-dimensional problem, again, because we already know how to do it, right? So we already know the setup here. So our volume function is x, y, z. Our area constraint, the function itself. So this is going to play the role of our f, to be optimized, right? To be optimized, and this is our constraint. So that'll play the role of our g. Our area function, remember, was x times y plus 2x times z plus 2y times z. Okay, and so now what do we need to do? Well, we need to set, the constraint was that this equals 12, right? So that's one of our equations. So here's one equation. One equation. The other equations are going to be from the gradient, right? So the gradient of f is equal to, on one, you just take the derivatives, right? So on one hand, it's y times z. The second component is x times z. The third component is x times y. All right, then we take the gradient of g. G is what we're calling the surface area function, right? So the derivative with respect to x of this function is y plus 2z, right? Y plus 2z. The gradient with respect to y, or the derivative with respect to y, is going to be x plus 2z. So symmetry there, that's no surprise. And then the derivative with respect to z is going to be 0 plus 2x plus 2y. So 2x plus 2y. All right, now we need to make our system of equations, right? This is one of our equations. The other three come from setting these equal but not exactly equal, right? We need the lambda. So gradient f equals lambda times gradient g. or it could be rearranged, but this is, we can do it either way. So gradient of f equals lambda times gradient g. This is going to give us the following system. So y times z is going to equal lambda times y plus 2z. X times z is going to equal lambda times x plus 2z. And then x times y is equal to lambda times 2x plus 2y. All right, now this is and then we still have this constraint up here, right? So xy plus 2xz plus 2yz has to equal 12. So don't forget this function. But let's focus on this portion of the system. So we have 3 equations and 4 unknowns, and these are nonlinear equations, and it's almost always going to be, because you're multiplying lambda by an equation. So there you've got nonlinear right away, right? We also have nonlinear over here, right? These are multiplied together. So nonlinear equations, nonlinear systems are a little bit harder than linear in the sense that there's not a systematic way to go about solving them in general. There's not just a general way. You can't write a matrix equation and then try to solve it, you know. Just doesn't work in general. So instead, what we can do on this one is we can notice that if we multiply this equation by x, multiply this equation by y, and multiply this equation by z, then we've got all 3 terms on this side are the same, and that means that we can equate these ones on this side, right? So we can set these equal. So multiplying through, and again, we're taking advantage of the same rule that we did before, which is that x, y, and z can't be 0, right? Because of the geometry and the physical nature of the problem, right? We're trying to optimize the volume of a box, so having a side length equal to 0 is not going to be the answer, right? So we can multiply through by these values and not worry about changing our answer. And then we get pairwise, we can set these equal to each other, right? So we get lambda times x times y plus 2z equals lambda times y times x plus 2z, right? Notice here, whatever lambda is, it cancels as long as lambda is not 0, right? So as long as lambda is not 0, then it's going to cancel. And by the way, lambda is not going to be 0 because just look at again, x, y, z are not 0, so therefore there's no way lambda could be 0 to satisfy these equations, right? So lambda is not 0, it cancels. And now this equation says x times y plus 2xz equals x times y plus 2yz. All right? X, y cancel, just subtract out. And then we have 2z, right? Again, z is not 0. Those divide through, and we get x equals y. All right? So there's one nice result there. So that's by using equations 1 and 2, right? We can use equations 1 and 3 and do the same thing. And so we'll get lambda x times y plus 2z equals lambda z times 2x plus 2y. And then, again, systematically kind of cancel stuff out here. The lambdas cancel. We multiply through. X times y plus 2xz equals 2xz plus 2zy. All right. Look what happens. This time, the 2xz's cancel, and then the y's cancel. And this time, we're left with, okay, x is equal to 2 times z. So now we have everything, or you could rewrite this as z equals x over 2, right? So now we've got everything in terms of x. And now we go back to our constraint. So at this point, we go back to this constraint, and we say, all right, our constraint was that x times y plus 2xz plus 2yz had to equal 12, right? We'll plug in these things for x. So this is going to be plugging in this and this, right, to our equation. We'll get this entire equation in terms of x. So if y is equal to x, this becomes x squared plus 2x times x over 2. So 2x squared over 2, right? Plus, this one's going to be y is equal to x, z is equal to this, right? So this is also 2x squared over 2. That's got to be 12. So 3x squared is going to equal 12. Well, that means x squared is 4, which means x is plus or minus 2. But just like we did before, we know that that's got to be positive, right? And then from there, we just use these equations to plug in. So if x is 2, y is 2. If x is 2, z is 1, right? And then our volume. Our volume is maximized at v of 2, 2, 1, which is equal to 4, right? So the maximum volume is 4. So this is a different approach, but it's the same result. And so the geometry of the situation is that we're looking for points where the level curves are tangent to each other. We do that by looking at the gradient vectors, right? Because the gradient vectors are orthogonal to the level curves. And then once we do all that, once we work that all out, we get the same answer, right? So we've optimized in a slightly different way. You can debate which way is quote-unquote easier, but they both gave the same answer, and they both worked out exactly correctly. So let's leave this lecture here, and I'll talk to you guys in the next one.